Okay, today's lesson is on half-life, and what we're looking at now is nuclear decay, and it's more of a math type equation. A lot of you might have done this in Math 30 if you've taken it. It's where we take a look at how much of an element decays over time. So when we use the term half-life, what we're talking about is how long it would take for that element to transmutate half of the neutrons or nucleuses. So if you're doing alpha and beta decay, remember we looked at yesterday where a chemical could transmutate to something else. So we want to know how long it would take for half of that element to remain the same. And then obviously the next half-life would be half of that again, so you get a quarter and so on. And each element has different time periods. Some of them happen almost instantly, so it could be anywhere from like 10 to the negative 22 seconds, and some of them take thousands or millions of years, so 10 to the 28 seconds. So the half-life is quite different for any chemical. And the thing to remember is the number of atoms still stay the same. We're not changing protons and neutrons and so on. All we're doing is we're sort of transmutating them from one element to the other. So if we're trying to measure the half-life of carbon, so for example, half-life of carbon-14, the elements are staying the same. It's just that carbon-14 is translating or transmutating into something different. So for half-life of carbon-14 is 5730. So that means that carbon-14 in 5,730 years, half of those original nucleons would then be gone. So if you started, let's suppose you started with 100 atoms. In 5,700 years, you'd have 50, and then in another 5,700 years, you'd have 25, and another 5,700 years, you'd have 12 and a half, and so on. It would just keep getting cut in half and half as time goes on. So because every element sort of has its own sort of time frame, we can use that half-life and work backwards to figure out how old certain things are. So if you find a dinosaur bone, we can measure the carbon-14, figure out how much of it is left, what it should have been, and we can backtrack it to figure out how old that dinosaur was when it was still alive. And as it undergoes decay, we can usually measure that activity. So we usually measure it as sort of how much decay there is per second, which is usually measured in becquerels, which is the amount of decay per second. And we measure this using a Geiger counter. So that's where you see on movies they have the little beeper thing that they kind of scan to see if there's any nuclear decay going on. And as time goes on, the number of nuclei drop to decay, so then the activity would drop as well. So here's a graph kind of showing the same thing we just talked about. So if we had 100 original nuclei in one half-life period, then it would be 50, and then it would go to 25, then to 12, and 6, and so on. It just keeps getting cut half and half. So we can actually use a math formula to calculate this. So the formula is n equals NO a half to the n, where n is representing the number that is left, and this can be measured in atoms, mass, grams, or any kind of unit. It really doesn't matter. And we just take the original amount times it by half to the exponent of however many half-lives there are. So for a question like we just looked at for carbon-14, we'd actually write it as 5730 divided by t. So depending on the time, so in 5730 that would be one half-life. So if you had two half-lives, sorry, I got this backwards, it'd be t over 5730. So if you had 10,400 years, you divide that and that would give you two half-lives and so on. So let's do an example. So in this case, he says we've got 765 grams of polonium, and the half-life is 138 days. So if we use our formula, so we'd write it as 765 is our original amount, half-life, and for our n, so we want to know 3.8 years later, so 3.8 years, we have to divide that by 138 days to figure out how many half-lives there are. So on your calculator, if you go 3.8 years, times that by 365 days in a year, that gives us 1387. So if we divide those, you can see it's roughly 10 half-lives. So we'd have 765 times 0.5 to the power of 10, or you can just type in 1387 divided by 138, and that gives us 0.72 left over. So this was original was in grams, that means we only have 0.72 grams left over. So what happened to the other 764.3 grams? So the rest of it got transmutated. So this is only how much polonium is left. Right, so the polonium amount is 0.72 grams. The rest of it, it could be any other kind of chemicals, uranium or whatever, but the rest of it is still there. It'd still be in the box, but it's no longer polonium. It would have transmutated to something else. So it'll be some sort of other element or elements. Okay, so let's do one more example. So this one we've got lead 212, and it says we've got 75 grams of it. So we have 75 as our starting amount. It says we have a half-life of 10.6 hours. So that means we'd have 10.6 on the bottom. So this question is sort of asking how long will it take in order to get 9.3 grams left over. So you can see in this case what we're doing is we're solving it for the time. So to solve this equation mathematically, just like any other equation, what we want to do first is divide by the 75. Okay, so divide by the 75. So if we go 9.3 divided by 75, that gives you 0.124, and that would equal half to the time over 10.6. So this is where we run into a little bit of a problem. If you haven't taken Math 30 yet, we can't solve for that exponent unless we use what we call logs. So what you want to do to solve this is just do the log of both sides. So we'd have log 0.124 equals log of a half to the t over 10.6. And then mathematically what we can do is we can divide. This t over 10.6 comes down in front. That's one of the log rules. So we get that. So to solve it for t, we'd have log 0.124 divided by log a half. We'll just write it as 0.5. That equals t over 10.6. So we can cross multiply. So you'd have 10.6 times log 0.124 divided by log 0.5. You can just type that directly in your calculator and it should be good. So log 10.6 times 10.6 times log 0.124, divide that by log 0.5, we get an answer of 31.9. So in 31.9 hours, then we'd be down to that amount. So we know that the half-life is 10.6, so if we can just use some logic, so in 10.6 hours, we'd have half of 75, so that's about 37. Then in another 10.6, that'd be like 21 hours. We'd have half of that, so we're down to about 18. And then in another 10.6, so now we're getting close to the 30, 31, 32 hours. We'd have half of that, which is about the 9. So it does make sense that it took 3 half-lives to go 10.6, 10.6, 10.6, which is roughly 31 hours. And that would get us down to 3 halves of the original amount. And that's all.